So now that we're more acquainted with the dot product, I want you to think back to an earlier video where we went over the basics of what a unit vector is, and I introduced to you I hat, j hat, and k hat. So once again, we're going to draw I hat, k hat, and j hat. Let me just get a coordinate axis on the grid. A coordinate axis drawn out in 3D space. Here's our z, here's our x, and here is our y. Let me just draw this dot. All right. So here is our y, here is our x, and here is our z. All right. And once again, just a refresher, I drew this last time. I mentioned the unit vectors. We have a unit vector k, and k only has a z component. We'll call this k hat. And if I was to write it up here, k hat can be described as 0, 0, 1. And let's say we have another vector going along the x-axis. Let me just rotate this 90 degrees. And it's the same length as k hat. And we call this vector I hat. And I hat has the components of 1, 0, 0, because it only goes along the x-axis. And we have another vector in the 3D coordinate axes of three-dimensional space. And we call this vector, first let me get it drawn out. We call this vector j hat. And j hat has components of 0, 1, 0. And that's because it only has a y component. And these are all orthogonal to one another. Notice, if you were to take the dot product of, say, I and k, you would get a dot product of 0, because you would do 0 times 1, which is 0, plus 0 times 0, and then plus 0 over here, because 1 times 0 is 0. They're all orthogonal to one another. See, this over here is a right angle. This over here is a right angle. So their dot products are always 0. And I also showed you that you can describe any vector in three-dimensional space as a combination of I hat, j hat, and k hat. But one more thing that we can note that we can use the dot product for now is to further characterize what a vector looks like in three-dimensional space. So let's say we have our good friend over here, v, vector v, and he is lying with his tip above this x point over here, or his head over here. And I want to show that vector v is making some angles with these unit vectors. With vector k, say he's making some angle alpha. With vector I hat, he's making an angle beta. Beta, anybody knows the angle beta, it's literally just the Greek letter b. And with vector j hat, that's this angle over here. It's a little tough to see, just because of the nature way I drew it. I apologize. This is angle gamma. It's literally just the angle between j hat and v, and this angle alpha is the angle between k hat and v, and beta is the angle between between unit vector I hat and vector v. So I can characterize vector v by these angles using the dot product. I'm just going to delete, actually, you know what? I'll keep that up there. Let's see how I can solve for these angles now. So I know that k hat is 0, 0, 1, and let's just write v for now. Let's keep this just, general. v1, v2, and v3. Now I want to find what v dot k hat is. Let's do that real quick. Let's find v dotted with k hat. And I encourage you, give this video a pause and try to find for me what v dot k hat is. Well, if you do this, it would be v1 times 0, which is 0, plus v2 times 0, which is also just 0, plus v3 times 1, just v3. So this answer would just give us v3. This would be the dot product of vector v with k hat. And I could also rewrite this, because remember our other definition of the dot product. This can also be written as the magnitude of v multiplied by the magnitude of k hat times the cosine of the angle between them. And what's the angle between them? That's none other than angle alpha. So let's see if we can clean this up a little bit more. I know that k hat is a unit vector. If I was to find the square root of 0 plus 0 squared plus 0 squared plus 1 squared, I know that magnitude of k is just 1. So now this simplifies to v3 is equal to magnitude of v times the cosine, let me do that in white actually, times the cosine of alpha. And I can solve for the cosine of alpha now, and I can therefore solve for what alpha is, the angle between v and the z-axis. All I have to do is just say that cosine of alpha must be equal to v3 divided by the magnitude of vector v. And this is how we solve for what alpha is. And I can do very similar reasoning. I try to find v dotted with I hat, and I would find that cosine of beta, I encourage you to just try this out. Do the same exact process, v dotted with I hat now, and I would find that cosine of beta would be v1 divided by the magnitude of vector v. And similarly, once again, I could try to find what angle gamma is. I would find that the cosine of gamma would be v2 divided by the magnitude of vector v. And all I'm doing here is I'm just using the definition of the dot product, our prior knowledge from the prior like 3 or so videos or so. And I'm finding literally just ways to find the angle between the x-axis and some vector, the y-axis and some vector, and the z-axis and that vector. And I can also just characterize this further. Let's say that vector, well, first I gotta delete some stuff. So make sure you have this stuff copied down and rewatch the video until you understand it. All I did was just take the dot product of vector v and one of the unit vectors. So let me just clear this out real quick. Make sure you have this, you know what, I don't think I'm gonna delete it. I'm gonna delete up here. I just need a little bit more room to get this next point across. And let me see if I can just get just this part deleted. Nice. And over here. And a little bit over there. All right. And let me just redraw that. I apologize if that's bothering you. Why isn't this going? There we go. All right. Now, let's say vector v was actually a unit vector. Let's say v had magnitude of 1. So this would actually simplify. Now, cosine of alpha would now be, because this would actually be a 1, this would be a 1, and this would be a 1, in the case that vector v was a unit vector. So now, cosine of alpha would just be v3. Similarly, cosine of beta would just be v1, and cosine of gamma would just be v2. So therefore, if I was to write vector v, which is given by just v1, v2, v3, I see that v1 must be just cosine of beta. So its components are its direct, we call these the direction cosines. cosine of gamma, and then its z component would be cosine of alpha. And similarly, I know that the magnitude of v, I'm assuming I'm saying in the case that v is a unit vector, is 1. So I know that square root of v1 squared plus v2 squared plus v3 squared must be 1. And I could also just write this over here as cosine of beta squared plus cosine squared of gamma plus the cosine squared of alpha must also equal 1. Because I know this because the magnitude of v is 1. And this is just literally just follows from the dot product. If you understand the previous two videos, this should be quite clear to you. And if you don't freak out. I just encourage you to just watch it over a couple more times and just understand it. So this is another way to characterize what a vector looks like in three-dimensional space, and we call these angles direction cosines because they tell us the direction that the vector is pointing in terms of the cosines of the angles that the vector makes with each of the unit vectors. So I hope this helps you, and I'll see you in the next video.